How do we measure a quantum qubit? Have you ever wondered how we can measure something as strange as a quantum qubit? It's a fascinating topic that combines the principles of quantum mechanics and information theory. Let's break it down in a way that's easy to grasp. When we measure a quantum qubit, we interact with its quantum state to pull out classical information. This process causes the qubit to change from a superposition of states into one of its basis states, usually labeled as 0 or 1. Unlike classical bits that are strictly 0 or 1, a qubit can exist in a mix of both states at the same time. The measurement gives us a result of 0 with a probability that is equal to the squared magnitude of the amplitude for the 0 state. Similarly, it gives us a result of 1 with the squared magnitude of the amplitude for the 1 state. This means that when we measure a qubit, we are dealing with probabilities, and the outcome is not guaranteed. The measurement process is irreversible. Once we measure the qubit, its state collapses to the observed basis state. Mathematically, this is described using measurement operators that act on the qubit state space. After we measure, the qubit state changes according to the result we observe. There are several techniques for measuring qubits, and the method often depends on the type of quantum computing platform being used. For instance, in a full system measurement, all qubits in a quantum processor are measured at the end of a computation to read out the final result. In contrast, a mid-circuit measurement allows us to measure specific qubits during the computation. This can help influence further operations or correct errors without disturbing the entire quantum state. Another interesting method is the Bell state measurement, which is used for pairs of entangled qubits. This measurement is vital in processes like quantum teleportation, where we need to measure the joint state of two qubits in an entangled basis. In practical experiments, measuring qubits often involves connecting the qubit system to an external measurement device. For example, in superconducting qubits, we might use microwave cavities to infer the qubit state by observing shifts in the cavity's resonance frequency caused by the qubit. For other types of qubits, like those based on photon polarization, we use methods like quantum state tomography. This involves taking multiple measurements in different bases to reconstruct the full quantum state of the qubit. Quantum state tomography is a method where we perform many repeated measurements in various bases. This allows us to build a complete picture of the qubit state beyond just the basic outcomes of 0 or 1. So, measuring a quantum qubit is all about converting its quantum information into classical information. This process is fundamental to quantum information theory and quantum computing. Understanding how to measure qubits effectively is essential for building reliable quantum computers and running quantum algorithms successfully.